Math 13 students, last bit of detail on section 5.2, the binomial distribution. We're going to take a look at calculating the parameters. That would be the mean, the standard deviation, and the variance. There are no special built-in tools to do this. We actually need the formulas, although they are not very difficult to use, to be honest. So follow me over to my other screen and we'll take care of business. All right. Section 5.2, binomial distribution, the parameters. We have some worked examples for you. In this presentation, we're going to review the definitions of the parameters. We're going to need the formulas, so we need to go over them. We'll calculate the parameters of a binomial probability distribution, and then we'll identify significant outcomes. We'll try to bring together two components. We'll try to bring together the range rule of thumb together with the notion of probability for identifying significantly high or low outcomes. And as we go through that detail, we'll look at appropriate examples. Now, we'll take a look at the parameters first. A binomial distribution has a mean, a standard deviation, and a variance, and it is treated just like a population. So we get the Greek notation, mu for mean, and sigma for the standard deviation, and sigma squared for the variance. Now, we're going to need these formulas. They are not hard to use. The mean, n times p. The standard deviation, the square root of n times p times q. You'll have to remember, though, that q is equal to 1 minus p. The standard deviation gives us the variance. If we square both sides, we'll have a variance equal to n times p times q. As I say, the formulas are very straightforward and easy to use. All right, let's take a look at our first example. Probability of guessing correctly in a multiple choice question is p equals 0.2. And we're going to take a test of 20 questions, and we're going to guess randomly on all those 20 questions. A little bit unrealistic, but it'll get the point across. We're going to find the mean number of correct guesses, the standard deviation for the number of correct guesses, and the variance for the number of correct guesses. Got to use those formulas, and we're going to need those values. N is equal to 20 because we're guessing 20 times. On any one question, the probability of guessing correctly is 0.2. That's our P. Q, 1 minus 0.2 or 0.8. Remember, P and Q have to sum to 1. Now, to find the mean number of correct guesses, N times P means mu is equal to 4.0 correct guesses. I take one more decimal place than the number of correct guesses, which is a whole number, so I take 1 decimal place. I'll find the standard deviation now. I'll need N and P and Q. They all live within the little square root there. 1.788 and change. 1.8 correct guesses is the standard deviation for this probability distribution. The variance. 20 times 0.2 times 0.8, 3.2 correct squared. Remember, the units are squared for variance. I have no idea what a squared correct answer is. It is an artifact of the calculation. Now, let's take a look at example number 2. Since the probability of guessing correctly on any one question is 0.2, and we have 20 questions to choose from, we're going to use that range rule of thumb to identify and interpret significant outcomes. I'll need the parameters, mu equals 4.0 and sigma equals 1.8. I usually use the rounded versions for this kind of calculation. More accurate would be to use the unrounded version and carry more decimal places. So I'll take the mean and I'll add and subtract 2 standard deviations. So 4.0 minus 2 times 1.8, a significantly low number of successes is 0. Well, that's what I round to after I get the 0.4. Or less. Can't have less than 0. And a significantly high number of successes is 8. Well, 7.6. Since I can't have 0.6 of a correct answer, I'll round that guy up to 8 correct answers. So if I'm guessing on 20 questions in this situation and I get 8 or more correct, I've done very well. I have a significantly high number of correct guesses. Now, example number 3, I want to remind people that there are 2 methods for identifying unusual or significantly high or low numbers of outcomes. We can use the parameter approach, where I take the values that are at least 2 standard deviations above and below the mean. Or I can use a probabilistic argument. If the probability of x being at least or at most a given number is less than 0.05, less than or equal to 0.05, then that set of outcomes is indeed significant. If I use the parameters approach, well, 8 or more, so at least 8 correct would give me a significantly high number of outcomes. Probability, well, this is a binomial distribution. I'm looking for the probability that 8 is greater than or equal to, probability of x is greater than or equal to 8. Now, I'll need to remember, and one of the reasons I've got this in here is to remind you guys of the keystrokes over here. I'm going to use that binomial distribution program again, and I've used it once or twice before, and I'm going to go over the keystrokes again. So I'll remind you the way it works. We can calculate the sum of many, if you will, from 0 up to a given number. If I need to calculate the probability of 8 or more, I use a complementary argument, and I'll take 1 minus the probability of 0 to 7 inclusive correct responses. Now, on my calculator over here, it's pretty straightforward. 1 minus, I'll go to distributions, scroll downstairs, basement, I guess. Oh, there we go, the cumulative distribution function. I'll remind people it needs the number of trials, then the comma key comes into play, the probability of p, comma comes out again, and then the number of successes up to and including, and in this case, 7. Close them up, blow on your calculator once for luck, hit enter, and I get a 0.321 and change. Coming back over to my PowerPoint, there's the detail. Now, I'll remind you also here about the rounding rule for probabilities. 3 significant digits. I go to the first non-zero digit. I'm going to take 3. 1, 2, 3. I take a look at that 1. I need to go 1 more out here to the 4. That tells me what to do with the 1. I'm going to keep the 1. So the probability is a 0.0321, and that is less than or equal to the 0.05. So you can see that those answers comport. They don't disagree. They really should give you the same result. You will run into issue with rounding on occasion, which is why sometimes when I use the range rule of thumb, plus or minus 2 standard deviations, I actually use the unrounded version in my calculations. But be that as it may, there we go. You've got an example now that shows you 2 different ways of calculating or interpreting significantly number of high or low number of successes. All right, I think that's pretty much it. We have reviewed those definitions for the parameter of a binomial distribution. We've calculated an example. We've identified significant outcomes a couple of different ways, and we compared the 2. And we included appropriate examples as we took this little journey together. So I'll leave you here because that is the end. I will stop the sharing, and I'll ask that you come and visit me during my office hours. Bring your calculator, bring your questions, and we'll make sure you can do the problems in your problem set. Thank you, and goodbye.